Welcome to Scale Models. I'm Jason, your host, and I do models and electronics and learning stuff from a book. What's going on? Oh no. It is chapter 2 in my digital logic series that I am learning from this fantastic book from Brock Lemire's Introduction to Logic Circuits and Logic Design with Verilog. This is the second edition book. We've already went over chapter 1, the difference between analog and digital systems. And in this chapter, I don't want to show any copyrighted material, but it is basically the number system and talking about converting between binary, what is binary, hexadecimal, decimal, and the octal system. I'm going to leave out the octal system because it's pretty old and not used that much, but I'm going to go over binary and hexadecimal. I'm not going to make this too long, I hope. I'm going to go to my pad here. So in the decimal system, we have 10 digits, and I'll just put right here DEC. In the decimal system, we have, wow, I just already messed up, didn't I? DEC, decimal. We have the digit 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That is our digits in the decimal system. And then you have the binary, where you only have two systems, hence binary. You have a 0 and a 1. And then you have the hexadecimal system, hexa, and then you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you have A, B, C, D, E, and F. So you have 16 possible digits in the hexadecimal system. And from my understanding, hexadecimal is mainly a way to shrink binary into four binary digits, or a number that consists of four binary digits, called a nibble. And basically, if you had 0, 0, 0, 0 in binary, that would be a decimal. So this is binary. Your decimal equivalent would be 0. And then your hexadecimal equivalent would be 0 also. But if you had 1, 1, 1, 1, your binary equivalent would be 15. And your hexadecimal equivalent would be F. So then if you had a 8-digit binary number, so if you had 1, 1, 1, 1, 0, 0, 0, 0, that would be the decimal equivalent to that would be rather large, so I'm not going to convert that in decimal. But if you break this down into two sections here, these two sections into hexadecimal, the first section would be F, and the second section would be 0. So in hexadecimal, that would be F0. And when we're programming, it's good to know the binary and how to convert from binary to decimal to hexadecimal. Binary to hexadecimal and hexadecimal to binary is a lot easier, in my opinion, than the binary to decimal or hexadecimal to the binary. So I am going to clear this, and then I am going to show you what I'm talking about. So if we have a number here, let's use an example. Let's just use an example here. So if we had a decimal number, say we have 132.654, and we all know that this is, if you use engineering notation, that this place right here is 10 to the negative 3, and this is in base 10 system. 10, I messed that up. 10 to the negative 3, This is a base 10 system. And then this one would be 10 to the negative 2 spaces. And this would be 10 to the negative 1. And then you have your decimal place or your radix. And then this would be, this right here would be 10 to the 0. This would be 10 to the 1. And this would be 10 to the 2, to the second power. So you're basically multiplying this first number. So it would be 1 times 10 to the second, or 1 times 100. So you would have 1 times 100 plus 3 times 10 to the first, so 3 times 10, plus 3 times 10, and then you would have plus anything multiplied by something to the 0 power is just multiplied by 1, so it would be 2 times 1, and then you would add this one, and then this one would be 6 times 0.1, and then this one would be 5 plus 5 times 0.01, and then it would be plus 4 times 0.001. And you would add all those numbers together. So you would add all those together, and you would have basically 100 plus 30 plus 2 plus 0.6 plus 0.05 plus 0.004, and that would give you the 132.654 in decimal format. So that's how you, we're not converting there, but that's how you would read out a number and apply the decimal system to the number. So that is basically how we work out these problems, but we use different base systems for this. So in a base 2 number, it's a little bit different. So you have, say you have 1, 0, 1, 1, oops, I messed that up, 101.11 and base 2. Now these are labeled a little bit different because the base is only 2, so instead of 10, we are going to use 2 for our base. So this one would be 2 to the negative 2, and then this one would be 2 to the negative 1, and this would be 2 to the 0, 2 to the 1, and 2 to the 2. So you would have 1 times 4 plus 0 times 2 plus 1 times 1 plus 1 times, this one would be 0.5 plus 1 times 0.250, or a quarter, and then you would add this up, and this will give you 5.75 in base 10. So there we go. We converted this into a base 10 number by using the base power system here, by labeling each position with a value, just like we do in the decimal place. We have 100.001, and then this is the tens place, or the ones place, the tens place, the hundreds place. This is the tenths, the hundredths, and the thousandths place. So it's the same principle. And if you look at the, let me clear this again. If you look at the digits for the twos place, you normally have numbers like, if you have, say you have 8 digits here, 1, 2, 3, there's that happens every day, 2, and then we have another 4, 1, 2, 3, 4, and then this would be, if you look at this, this would be 2 to the 0, 2 to the 1, 2 to, let me make some more room here. This would be 2 to the 0, this would be 2 to the 1, this would be 2 to the 3, or 2 to the 2, and then this would be 2 cubed, 2 to the 4th power, 2 to the 5th power, 2 to the 6th power, and 2 to the 7th power. So if we get our handy dandy calculator out, because I do not know all these in my head, y'all. So if we come to our calculator here, and we have, not E, if we have, well, 2 to the 0 power is 1, so that one is 1, and then we have 2 to the 1st power is 2, 2 squared is 4, 2 to the 3rd, so 2 times 2 is 4, times 2 is 8, and we have this, so 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and then we have 2 to the 5th, 2 to the 5th, yeah, that's not what I'm looking for, 2, I want to raise that to the 5th, is going to be 32, 32, and then we have 2 to the 6th is 64, and this is 128. So this would be a 128-bit number. So you would basically, if you wanted to convert this number, say, you would add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which I believe is 256. Let's double check that. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. So it's 256 different numbers, because it goes from 0 to 255, which is a total of 256 bits of information that can be stored in a 8-bit number, and that would be considered a byte. So so that is how that works. And then for your, let's clear this one more time, let's clear this again. So, and then for your hexadecimals, you have, let's just make a table here. So in binary, we would have, we're going to do just 4-digit binaries. So we would have, if we count it up in binary, we would have that. And then we'd have 0, 0, 0, 1. So that is represented as 1 in decimal. We have 0, 0, 1, 0. That would be 2 in decimal, because we have 1 in the 2's place and 0 in the 1's place. So that's there. Then we want to go to the next. We go 0, 0, 1, 1, because we have, that would be 3, because we have 1 in the 2's place and 1 in the 1's place. We add that up, we have 3. Then we would have 0, 1, 0, 0. 1 in the 4's place is 4. We have 0, 1, 0, 1. 1 in the 4's, 1 in the 1's place is 5. 0, 1, 1, 0. That would be 1 in the 4's place, 1 in the 2's place. So for 6, we have 0, 1, 1, 1. So 2 plus 4 plus 2 plus 1 is 7. And we have 0, oops, nope, see, I already got ahead of myself. We have 1, 0, 0, 0. That would be 1 in the 8's place, so 8. We have 1, 0, 0, 1. So 1 in the 8's, 1 in the 1 is 9. Then we have 1, 0, 1, 0. 1 in the 8's, 1 in the 2 for 10. Then we have 1, 0, 1, 1. 1 in the 8, 1 in the 2, 10, and 1 more is 11. So then we have 1, 1, 0, 0. So 1 in the 8s, 1 in the 4 place, so that's 12. We have 1, 1, 0, 1, that's 13. We have 1, 1, 1, 0, that's 14. And then our last one is all ones, which is 15. So 8 plus 4 plus 2 plus 1 is 15. So that is our binary to 15. That will be your 4-bit binary nibble, as they say. And if you wanted to translate that in hexadecimal, you would have 0 for this one. You would have 0 in hexadecimal here. You would have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. So that would be your hexadecimals. So if you have a really unruly number in binary that has, like a 16-bit word, which would be 2 8-byte segments, two 8-byte numbers, which would be 16 digits long a word, you could simply express that as like A1C D. And then if you translated that, A would be 1 0 1 0, and 1 is 0 0 0 1, and C is 1 1 0 0, and D is 1 1 0 1. So A1CD in hexadecimal would be that number in binary. Now, if you wanted to convert a number like 1 0 1 0 1 0 1 1 1 0 1 0 1 1 1 0. So if you have that number, what I do is I break it into 4-bit sections, and then I come in here and I write down, okay, 1 0 1 0 1 0 is A, and then I have 1 0 1 1, that is B. Then I have 1 0 1 0, that is A again. Then I have 1 1 1, that is E. So this in hexadecimal would be A, B, A, E. So that is A babe. There you go, A babe. So that is basically how you can convert back and forth from hexadecimal and binary, and that is mainly what I will be using if I need to convert to decimal to hexadecimal or binary system. I will use a calculator because it's pretty simple, but you can use the base powers of 10 to do that process. And you can also convert from hexadecimal to hexadecimal to decimal. And to do that, you do the same thing. So you have A1C C D point F E. So instead of 2 or 10 in these power places, this one would be 16 to the negative 2. This one would be 16 to the negative 1. This would be 16 to 0, 16 to 1. This would be 16 to 2. This would be 16 to 3. And then you would multiply, this value. Now you need to know this value here, and we know A is 10, so this would be 10 times 16 to the power of 3 plus 1. We know 1 is 1 in decimal, so then we have 1 times 16 to the power of 2, and then we would have C. Well, what is C? So C is 10, 11, 12. C is 12, so we'd have 12 times 16 to the first power. Then we'd have D. D is 13, so we'd have that plus 13 times 10 to the 16 to the 0, sorry. Then we'd have f is 15, so 15 times 10 to the negative 1 times 16 to the negative 1. Wow, I'm getting this all messed up. Plus f is, or e is 14, 14 times 16 to the negative 2. And we add all that up, and this is where I would use a calculator, because now I can put this in here because I can do it longhand, but why would someone want to do that? So we have 10 times 16 to the third, oops, plus 1 times 16 to the second power, and then we have that is plus 12 times 16 to the 1 power, and then we have that is plus 13 times 16 to the 0, and then we have plus 15 times 16 to the negative 1, and then we have plus 14 times 16 to the negative 2, and we press enter, and we get a incredibly messed up 10 base 10, and it is 4142 1.992187, and that is crazy. If you want that in engineering notation, how I work, 41.4219921875 times 10 to the third, or as the calculator writes it, e to the third. So it's a pretty big number. And again, if you wanted to convert that into binary, we've done that before. A is 10, so A is, let's not worry about that. So I don't want to make this video too much longer. So that is the number system, and that is basically how you convert. You can convert back by doing division problems, by having a number and dividing it into 16 and converting that way. But I just tend to convert between the numbers with a calculator or things like that. But you do need to know how the system works and how to enter it in the calculator. My calculator, I can enter a hexadecimal number and press convert to binary or convert to decimal, but it is good to know how it works, and it does get you, a little bit familiar with some engineering notation and things like that. So that is going to do it for this video, guys. You can check me out, my links on social media. You can also check me on Patreon, where I do post things at no need to sign up, just to share with you guys. Be sure to check out this book. It's fantastic. It's Introduction to Logic Circuits and Logic Design with Verilog by Brock Lemires. He's fantastic. He has a YouTube channel, Digital Logic and Programming. Check it out. It's fantastic. Thank you so much, and have a fantastic day.